Welcome back to a bit more algebra. In this video, we are going to make an introduction to partial fractions. Basically, an algebraic fraction like this one can be split into or more fractions. These are called as partial fractions. For example, in this case, we can write this as a over x minus 3 plus b over x plus 1. This is always addition. In algebra, the terms are added. We only have the negative of a term added, which results in a simplification of subtraction. So you will never see here a subtraction sign. This will always be an addition initially, but later on, if you find b to be a negative number, then certainly this sign will change to minus. So this is one type of partial fractions. So this can be written as a over x minus 3 plus b over x plus 1. Now here, writing the denominators in this order or vice versa does not make any difference. So we could write a over x plus 1 plus b over x minus 3. That's totally fine. But note that you should have a factored form in the denominator. And this means if you don't have a factored form, you have to factorize that expression so that you can write the partial fractions. A second type of a partial fraction is when you have a repeated factor in the denominator. You can see that we have x minus 2 squared. So we're not going to write it as a over x plus 1 plus b over x minus 2 squared. We're going to add another fraction here. It's going to be c over x minus 2 squared. Let me explain the reason in a simpler way. Suppose that we have 13 over 24 and we'd like to write this as a partial fraction decomposition. And the first thing I have to do is to factorize 24, which will be 8 times 3, which is 2 cubed times 3. You see, we have 2 repeated 3 times as a factor. Now, I don't know which fractions are added to get 13 over 24. It could be a fraction with a denominator 2. It could be a fraction with denominator 2 squared, which is 4. Or it could be a fraction with a denominator 2 cubed, which is 8. By looking at 13 over 24, I can't tell which or if all of these fractions are involved in this addition. And certainly there must be a fraction with the denominator 3, so that we are going to end up with 24. That is why I have to consider every single possibility, like either I have this, or I have these two together, or maybe I have all these 3, maybe I have only these 2. We don't know. So we have to consider all the possibilities. At the end of the day, what's going to happen is if a fraction with a denominator 2 does not exist, we are going to find a to be 0 anyway. So the same thing applies to this fraction. When I'm writing the partial fraction decomposition, I have to consider both partial fractions, this one and this one. I don't know by looking at this fraction which of these fractions exist in the addition. Now, these two examples, this one and this one, these are proper fractions, which means they're not top-heavy. The expressions at the top are not bigger than the denominators in terms of degrees. Let me write an improper fraction and you will see the difference. So as you can see, we have x cubed at the top and x plus 1 times x minus 5 at the bottom. So the index of the term at the top is 3, which we call it as degree. So this is a third degree expression. Whereas if you expand this, you're going to end up with x squared plus or minus whatever, something, where the term x will have the biggest power being 2. So this is a second degree expression. Actually, these are polynomials when you expand them. So these are polynomials, and this is a third degree polynomial. This is a second degree polynomial. So it is top heavy in terms of degrees, and we call these as improper fractions. Now, when we start writing the partial fraction decomposition of such improper fractions, we start with ax plus b plus, then we start with the fraction part, which is going to be c over x plus 1 plus d over x minus 5. Now, the reason is, if you do long division, you're going to get an answer to this. Let's see. Now, you can see here that when you do the division, you end up with x plus 4, an expression without denominator. So this is not a fraction here. That is why we have to include ax plus b here. Now, how will we know that it's going to be ax plus b, but not, for example, ax squared plus bx plus c? So how am I going to know? Well, simply put, this is a third degree expression because the biggest power of the unknown is 3. And when you expand this expression, you start with x squared plus something, and you know that the biggest power of the unknown is 2. So this is a second degree expression. Hence, if you consider this as simple as x cubed over x squared, you will see that you're going to end up with x, which is a first degree expression because the power is 1. That is why we have to write ax plus b. Similarly, if we have a fraction like this, then you can see that this is a degree 4 expression because the biggest power for the unknown is 4 and the biggest power for the unknown is 2. So this is a second degree expression. So if you consider this as simple as to the power of 4 over x squared, you will end up with an x squared expression for sure. So you should be using a quadratic. Most probably, within the scope of P4, you won't end up with a quadratic like this. It's always going to be a difference of 1 degree between the numerator and the denominator, so you will write ax plus b only. However, it is good to know how you end up with these expressions here, just in case. Now, so far we have seen the denominators to be factored forms, and we said if they are not in factored form, factorize it. But we know that there are expressions which cannot be factorized. For example, this fraction. Now, we don't care what we have at the top. The most important part is this one. X squared plus 3 cannot be factorized. So we have to write this fraction as ax plus b, because you see that this is a degree 4 expression and this is a degree 3 one, because x times x squared will give you x cubed. So you must have ax plus b in the beginning. And then you will start with c over x minus 6. And the next fraction, the last one, will be dx plus e over x squared plus 3. Now the reason is, as in normal division, the remainder being less than the divisor, you must have this remainder, because that's the remainder, less than the divisor. This is dividing the expression, right? So if you're dividing by a second degree expression, you can see that this is x squared, your remainder must be a first degree expression. I mean, the degree of the remainder must be less than the degree of the divisor. Actually, that's why we are writing c over x minus 6 here, because the degree of x minus 6 is 1, because it's x to the power of 1. Therefore, this must be a remainder of degree 0, which is c times x to the power of 0. Well, any number to the power of 0 is 1, so we don't write this down, we just write c, but that is the reason. So basically, if you end up with an expression which cannot be factored in the denominator, then you have to consider the top part of this partial fraction, where the denominator is this one, to be one less degree. So it's going to be dx plus e here, because this is x squared plus 3. If it were x cubed plus x squared, I don't know, something that you cannot factorize, then the top part, the numerator, must be ax squared plus bx plus c, because that will be the remainder. I mean, we're talking about remainders when we apply long division of this divided by this, right? And we are using partial fraction decomposition just to avoid applying long division. And also, speaking of the use of partial fraction decomposition, we will be using partial fractions in integration as well. On another note, this type of fraction and its partial fraction decomposition is not included in the syllabus, but I'm including this again just in case. Now in the following videos you will see how to decompose these fractions into partial fractions, namely how to find a, b, c and such. Thanks for watching.